We're going to finish up searching and sorting, but before we do, we have a special guest from one of their student organizations, Corn Hacks. Corn Hacks has been around for quite a while now, 6 years?
Yeah.
Is this going to be the sixth one or the seventh one?
I believe it's the sixth one.
Sixth one? Okay, so this will be the 6th year. It's an annual hackathon, and go ahead and take it away.
Sure. Yeah, so I just wanted to let everybody know about this if you're not aware. So, like Dr. Brick was saying, we're an annual hackathon on campus for the School of Computing. It's totally free to attend, and we provide free breakfast, lunch, and dinner for all the participants. It's on campus, and it runs 24 hours over a weekend, Saturday to Sunday. It's going to be February 4th and 5th of next year, and our registration just opened. So this is our website. It's unlcornax.com. There's also an announcement in the weekly newsletters, and you can go here and register using that register button. But yeah, there will be free food. There will be employers there that are attending. It'll just go to this Google form, and you can talk to the employers there. Those are our sponsors, and they can talk about internships and careers. And then we also have prizes for the winners. In the past, we've given out iPads, keyboards, drones. It'll be about $3,000 worth of prizes. So yeah,
What's the theme this year?
So yeah, the theme this year is going to be cybersecurity. And then we also have 2 tracks, which are hardware and business. So if you do a project related to those, you can win additional prizes. But you don't have to follow the theme or the tracks at all. You can build pretty much whatever you want. It can be software, hardware, an application, a website, pretty much anything related to computer science. We've had virtual reality, handheld devices, applications like I was saying before. So it can be anything. You can work in up to teams of 4, or you can work by yourself. If you don't have a team, we can help you find a team the Friday before the event. So yeah, if you're interested. This is kind of what it looked like last year. The team sessions on Friday, then we have events going through Saturday, and then judging early Sunday, where you can win prizes.
But this year it's not January, it is.
This year it'll be the first week of February. That's the second weekend once you get back from winter break. Yeah. Anyway, if you have any questions, feel free to contact us. It's all on this page here, as well as pretty much everything that I just said. So, yeah. Any questions?
Don't look at it. Oh, I've only been through one class, and you'll be competing against seniors that have had 3 years or something like that. I don't know if you have tiers that you based on experience, but it doesn't really matter. You don't go into it thinking that you're going to win. Go into it thinking that you're going to learn something, and that you're going to have fun, right? Especially if you like that kind of 24-hour pressure. You don't have to stay up for 24 hours, by the way.
Yeah.
You can come in and work for a couple hours and go to sleep, and you come in and come back, go in, go out as much as you want. Come in just for the food, build something partially, and even if you don't complete it, at least you tried.
Yeah, exactly. It's a great experience just to learn something new over the 24 hours. And even if you don't win, you'll still get the free food. And also we have free swag for everyone. We give out t-shirts, bags, hats, stuff like that for everyone that participates. It's usually about 100 to 150 students, and it'll be on campus. So yeah. Usually it's in the Johnny Carson Center, which is just down that way on campus. And that's where we're planning on having it this time as well. So.
Any questions?
Great, thank you.
No questions online, so I'll be posting details about this as well in our weekly reminder, and you'll see it again and again in bits and bytes up until the date that you have to register. So 6th annual one, it's pretty mature now. Really consider going into it, even if you don't plan on building something huge. Use it as a fun learning opportunity. Thank you. All right, so today we're going to finish up with searching and sorting. We left it off last time where we had built a comparator for books, and then we replaced our functions that found the best book and found the worst book with a solution that simply sorted them in descending order according to the rating. So that way we knew that the best book was at the top because it had the top rating. The worst book was at the bottom because it had the worst rating, right? So what we're going to do now is we're going to replace that other part of our demonstration from way back when, where we went through and found all of Frank's books. All books by Frank Herbert here. Now, there were 5 or 6 books already. What I'm going to do is I'm going to change that exercise just a little bit, right? So instead of searching for all of Frank's books, we're just going to search for one of Frank's books, okay? To do that, I'm going to create a dummy key, just like you did in your lab yesterday for Cubs teams or California teams. What that means is simply that you don't care about the other aspects of that object. You just care about what you're searching for. In this case, I'm searching for Frank Herbert. And so I set the first name and the last name. I don't care about the birth date. And I've got an author here that I put into a book so that I can search for it, okay? Now, how do I go about searching for it? So we've got a binary search algorithm over here. I want to use that because I don't want to reinvent the wheel. I don't want to redo everything, right? So let's go ahead and call bsearch on this, right? The book that I'll find is a Frank book, like one of Frank's books, right? Is equal to a call to bsearch, right? Oh, here I called it result, right? So I'll just call it result there as well. And I'm going to call bsearch. Remember, what do you provide to bsearch here? There's the key, the array that you're searching for, the number of elements in the array, the size, the number of bytes that each one takes, right? And the comparator that you want to use to search. So the first thing I want to give it is my dummy key. Is that correct right there? I'll do the rest here in a second. Does it expect a regular old structure here? Nope. What does it expect? A pointer to a structure. How do I take a regular old structure and turn it into a pointer? Ampersand. Right, there we go. Otherwise, I'm going to search the array called libraries, right? Or libraries, excuse me. Right? And let's see, what else do we have up here? Where's my Q sort? There we go. Library, num books, and size of books, and then the comparator that you want to use. I'm just going to go ahead and copy all of that. Library, there we go. Now, is that going to work? Why is that not going to work? Why did it not work to search for California on that first exercise in your lab yesterday? It wasn't sorted in the proper order, right? It wasn't sorted by the same criteria that you're searching for. So let me go ahead and change this. If I want to search by author, right, because I've set up this dummy key for Frank Herbert, right, what do I need? I need a comparator for authors, CMP by author. Now, did we write that comparator yet? Nope. So we need to do that. We did write something kind of like it, right? We wrote this function called author is equal. Given a pointer to 2 different authors, it returns true if that author equals to that author. Is that a comparator? Nope. It doesn't. It's really far from following that pattern. It's only a comparator if it returns an integer and takes 2 const void pointers. That is the only thing that is a comparator. Okay? So let's go ahead and copy paste this. This is a comparator for book structures that orders them by author. Right? First name, or last name, excuse me. Last name, first name. In ascending order. What does ascending mean with respect to strings? Alphabetical order, A comes before B. Unfortunately, with lexicographic now, also caps come before lowercase, right? That's not going to be that big of an issue with names because all proper names are uppercase. It might be an issue with names that have spaces in them or something like that, but we're going to get lexicographic. It's, as long as there are only characters, we could ignore the casing if we wanted to, and we could do it that way. But I'm just going to go ahead and go with lexicographic. Can I call it by rating if it's by author? Nope. Author. There we go. CMP books by author. Now let me come back over here and change that. So CMP books by author. All right. Well, if I'm going to search by it, what do I need to do before? Oh, I haven't completed it yet, so we'll do that here in a second. But if you're going to do a binary search using one comparator, what do you need to do before you do that binary search? It needs to be sorted. Q-sort. And it's all the exact same stuff. Right? It is the array that you're sorting, the number of elements in that array, the number of bytes in that array that each element takes, and then finally the comparator that you want to use. Okay? All right, so let's actually write this now. What would it look like? I'm going to steal some code up here. The first thing that you do in any comparator is you force them to become the types that you're comparing. Right? Done. Right? Now I want to compare their author's first name, or last name, and then first name. So if we have the same last name, right? Herbert, 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 those should all be equal. But then you would, if they're equal, then you need to go to the first name, because Frank Herbert is not the only person named Herbert in the world, right? His son was also an author, Brian Herbert. And so if you've got Herbert, comma Brian, and Herbert, comma Frank, it should be in that order. So let's look at their last name first. So compare X's author's last name to Y's author's last name. Right? I'll put that into a comment here. How do I do that? How do I get X's author's last name? X author, right? That's what a book is. A book is an author right there. Now what do I do between them to access the author? Is it the dot operator or is it the arrow operator? Arrow, why? What is book here? What is X? It is a book pointer. When we have a pointer, what do? Arrow operator. Now, once I've gotten the author, is the author a pointer? Nope, it's a regular old structure. So to access its last name, it would be dot last name. Right? And compare that to Y's author's last name. Both of those are strings. How do we compare strings in C? strcmp. Right? That will return something negative, 0, or positive, depending on the relative ordering of their last names. Just making sure that I have the string library here, and I do. Right? Let's put that into a result. Int result. Okay. Now, if they have different last names, Adams and Herbert, right? We've already distinguished them. Adams comes before Herbert, right? Zoe comes after Herbert, right? If it's not equal to 0, then we're done, and we return. If not 0, right? Then return result. But if it is 0, we've got a tie. If result is 0, then we need to resolve that tie. Herbert, Herbert. We now need to look at the first name. Right? How do I compare their first names? Let me copy paste this code here. Don't forget that semicolon. Right? And I look at the first name. Right? And then compare it to the last name. Is that right? Here I compared apples to apples. Am I comparing apples to apples here? Nope. So again, be careful, be judicious with your copy pasta. Right? Make sure that you're always changing everything that needs to be changed. All right, put that into result. Excellent. Now, if they've got the same last name and the same first name, Herbert, Frank, how do we resolve that tie? Did anybody tell us how? Did we put that in the documentation? It just said author. For all intents and purposes, that author is the same. So just let it be. Return the result. It's going to be 0. Frank Herbert is the same as Frank Herbert. Now, if you wanted to resolve that tie, what could you do? What else is in a book? Title, release date, rating. Right? So to break that tie, what could we look at? Maybe the title, right? And what would that look like then? Let's go ahead and take this and make a new comparator. CMP books by author, then title, right? All right. Then that's more descriptive. If you just care about authors, fine. but if you care about authors and then titles, then great. Would we have been able to use that comparator here? No. What would it be searching for? What title would it be searching for then? The book record with no title, right? And that's not what we want. So you have to be very, very careful about what comparators you write and what comparators you use and how you resolve those ties. Let's go ahead and do this because I will want to do this in another exercise here, right? So, if we've got a tie based on the first name, if result is still 0, right? Then go ahead and set result equal to not their last name, not their first name, but the title and the title. Right? There we go. All right. What if I want to resolve another tie? So Frank Herbert's Dune. Right? You could have more than one titles with Dune, right? Why? Because that's how editions work. The first edition, the second edition, the third edition, they all have the same title. Right? Now, the way that we designed our book data structure up here, there's no way to resolve that. Right? In real life, how do you resolve ties? You go to some universal identifier. With respect to books, what is the universal identifier? The what? You could do the Dewey Decimal would be a categorization, so I think that all like non-fiction or all fiction books, sci-fi books would be like very narrow, right? And in fact, all the Dune books would probably have the same Dewey Decimal and even Library of Congress designation, right? Because they're all about the same thing. Right? How do you uniquely identify books and editions? No? ISBN? International Standard Book Number? Right? What about other things? What about people? What about in the United States? How do we uniquely identify people? Social Security numbers, right? Those are what are called surrogate keys, right? Those are natural keys, right? Things that exist external of our system and provide a unique identifier. Every time you publish a new edition of a book, you have to register with ISBN, the ISBN registry, and you have to actually pay for it. It does cost you to register a book or a publication. What about movies? Movies or published media like that? I think it's an EIDR. EIDR, there we go. The Universal Media Identifier, right? So there are various standards like this that you can use and you can reference to actually break those ties. I'm not going to get into it that much, right? There's no way that we're going to break that tie unless we bring in that data, right? But I do want to clean up this code, right? If I went through this route and I broke a tie, right? If I went this route, I would need to nest. Right? That's ugly. Do I actually need to nest this statement here? This is equivalent. Right? If I just move it out here. Right? So if you have a tie, then break it this way. If you still have a tie, then break it this way. If you still have a tie, break it that way. Right? That relying on the linear control flow leads to much cleaner code. Now I don't have to nest things. Right? Excellent. Now I've got this comparator as well. Make sure that I'm going to go and make sure to put the header over here, and let's test it out. Remember, what I'm doing now is I'm finding a book by Frank Herbert, and if it's successful, then it'll print it out. Otherwise, it'll print out null. Lecture CSE 155H. Oh, sorry. CSE 155. There we go. GCC book.c and book demo all together here. Ignore those warnings. There we go. There, we found a book, Children of Dune. That is indeed one of Frank's books. Was it the first book in the ordering there? Nope. Did it have to be? No, I just wanted a book. But now let's go back to this original problem that we had where we wrote a function to get all of the books by Frank Herbert. How could we potentially simplify that implementation now? We won't do it here today, but you could potentially simplify it. If you ordered everything by author, where are all of Frank's books? Right here contiguously. If you found one of them, what would you have to do to find all of them? Just simply expand your search up here and expand your search down here and find the range in which all of Frank's books exists. Right? Now it's a much easier problem because you're leveraging quicksort and you're leveraging binary search. Right? Okay. Any questions so far? No? What else then? What else could we do? Release date. I don't want to do that. Why? What would that look like? I'd have to make sure that there's a tiebreaker based on years. Then if the years are the same, I would have to make sure that there's a tiebreaker based on months. If the months are the same, tiebreaker based on days. So just a bunch of if-else-if statements. Okay? Otherwise, that looks good. I don't want to do any more. Do you? It's all pretty straightforward. What I do want to do is talk about some miscellaneous issues here, right? One of them we've already talked about, right? Total orders. Right? Sometimes you want to write comparators for only one or a subset of member variables or data, right? Other times, you want a total order, right? In other words, there is no possibility of a tie, right? To do so, you need to establish a universally unique identifier. So for example, ISBNs, right? The EIDRs, right? Social security numbers. These are all what are called natural keys. Right? Sometimes there is no natural key. Natural key. Or it's too hard to get one. So alternatives would be to generate natural surrogate keys. Right? Typically, this is done in a database. Databases will typically handle key management for you. Right? Every time you put in a new record in the database, it'll automatically generate what's called a primary key, a unique primary key for you. And it'll do all the key management. It'll make sure that any new record that comes in is never given the same value as something that already exists. Right? Every time you delete it, maybe that key then becomes available for the next guy that comes in. Right? But the database management system will take care of that for you. Otherwise, UUIDs are really nice. Right? So what are UUIDs? UUIDs are universally unique identifiers. They're cryptographically based. Basically, what do they look like? Here we go. Here's what one looks like. Let me zoom in. There we go. Right? There's what a universally unique identifier looks like. There's a little bit of randomness. There's a little bit of you mix in the system time. You mix in a little bit of randomness. Then you mix in a little bit of cryptographic functions to scramble it and randomize it. And the probability that anywhere in the world at any point in history, two computers will generate the same UUIDs is infinitesimally small. It's still possible, right? And of course, you could always take that UUID and copy it, right? But that kind of defeats the purpose. But the probability that two random computers anywhere in time will generate the same UUIDs is extremely small. So this is pretty safe to use as a surrogate key. Right? Typically, you would use a library to do something like this. A library to just generate a random UUID. Right? Online, generate UUID. Right? Online UUID generator. Cool. Generate one. All right. Oh, there it is, right there. And then you can copy it over, right? You can generate 500 of them. All right, generate all of those. What does it look like? There we go. And they're definitely unique. Now, a lot of them have the same part here. I imagine that part is part of the timestamp or something. But otherwise, the rest of it is some cryptographic function that's being used and some cryptographic hash function. Kind of like NFTs and Bitcoin and all that crap. Right? But these are actually useful. Right? All right. So another miscellaneous item is, which one do I want to do first? Sorting, artificial versus natural sorting. Artificial, there, sorry, terrible speller. For that, I'm not going to actually do any coding here. Instead, I'm going to come over here to a demonstration. Okay, let me zoom in on this. So I've got a roster of data here with first names, last names, students, NUIDs, emails, this is all fake by the way, and years, okay? Now I want to sort them by their year. Before I hit this button, let's predict over here what the year should be. I've got freshmen, sophomores, juniors, and seniors. What should the order be? Okay, you're going in descending order, right? So seniors, then juniors, then sophomores, then freshmen. I think the way I went was youngest to oldest. So freshman, sophomore, junior, senior. Now before I hit this button, right, I'll tell you that that's how I programmed it, right? But if you were to use, say, strcmp and C on sophomore, junior, senior, freshman, what is the order? Freshman would end up coming first, like normal. Why? Because it begins with an F. But then what comes next? Junior. Is that correct? Nope, that's lexicographic, right? So if you're looking for lexicographic order, sure, certainly. But that's not the order that you mean. The order that you mean, or the order that you actually want, is probably freshman, sophomore, junior, senior. That's called an artificial ordering instead of a natural ordering. The natural ordering, of course, would be lexicographic. Artificial ordering means that you use some other criteria, right? You use some human-oriented criteria to sort, right? That means you cannot rely on built-in functions such or operators such as strcmp or less than, greater than, etc. Right? So what are you going to do? Let me come back over here to this example, and I have no idea how that happened. Cool. Anyway, I don't know. Was that always up there? Okay. All right. Whatever. Anyway, how do you think I programmed this? Well, one way that you could program this pretty easily is just take A and B as strings. Freshman comes before junior, right? But junior comes before junior comes before senior, right? And then sophomore comes before junior, right? And you've got 4 of these things, and you're comparing 4 other possibilities. How many possibilities are there now? Not 8. 4 possibilities for the first one, 4 possibilities for the second one. We've got a total of 16. Do you want to write 16 if-else-if statements? I don't, because what happens when you bring in graduate students? What happens when you bring in another one, right? You've just blown it up by another factor. 5 versus 5? Now how many do you have to write? 25. 6, 5th year senior, right? There we go. Still eligible, right? Now we've got 6. 6 times 6 is 36. Now we've got 5th year senior plus COVID eligibility. And we've got 7 times 7. 49 if-else-if statements? No, right? What's another way that we could do this? An enumeration. Excellent. What would that look like? How do we do enumerations in C? Type, def, struct, right? And if I want a freshman, they come first, right? What number is that given by default? 0. What number is sophomore given? 1. In other words, these are now orderable, and you can use these comparison operators, right? And then what happens when a grad student comes in? You just put them last, graduate. What happens when, I don't know, pre-freshman comes in? You just go ahead and change your list to be pre-freshman, right? And your logic in your comparator doesn't change. Right? Very cool solution, right? A very simple solution to an otherwise inelegant problem here. Right? All right, so another solution is to create an enumerated type or some data structure. For example, if this was Java or Python or something, what I would do is I would create a dictionary or a map instead, right? But for C, we don't have those things, so an enumerated type is the solution I would go with to define the ordering. Right? Then you can use less than, greater than, and equals, not equals, etc. Right? Nice solution, okay? The last thing that I'll bring to your attention here is oftentimes you want to do sorting by two categories. For example, if this were an Excel file and you wanted to sort it, you went up there to that button and you clicked sort, a dialog would come up and say, what do you want to sort by? Well, I want to sort first by GPA, right? There we go, in ascending order. Okay, so low GPA to high GPA up here, right? But then, I want to separate all the freshmen, all the sophomores, all the juniors, and the seniors, and then I want to retain that original ordering of GPAs because I want all the freshmen low GPA to high GPA. I want all of the sophomores low GPA to high GPA because I want to award freshmen only scholarships for high GPAs. Right? So I want to filter those out, or at least sort them and look at only the freshmen, and then start going down the list of GPAs. Right? So you sort by one, and then in Excel you have this little button here that says plus, and you can then sort by, right? And what generally happens is that it will retain the original order. In other words, we've got low GPA to high GPA. If I now sort it by year, I'll get all the freshmen at the top. But will it necessarily be the case that the GPA orders will be preserved? Let's find out. Right. Unfortunately, I think it is. Is it? Okay. Anyway, that was successful. All right, well, I'll show you one that's not going to be successful here in a second. That's called sorting stability. A sorting algorithm is stable if the original ordering of otherwise equal elements is preserved in the final sort, right? In other words, if you have something like this, say 2, and what I'll do is I'll subscript this with A, it came first, then 1, then 2B, and then, 4, right? Sort that for me, right? Both 2A, or 2A, 1, 2A, 2B, and 4. And I don't want to retype this, so cut, paste, switch around B, and switch around A are sorted. Right? But the first is stable. The second is unstable. Why is it unstable? Because, oops, did not mean to highlight all that stuff. Because the original 2 and 2 are equal, but 2A and 2B, they appeared like this originally. If they stay like that in the throughout the sorting algorithm, then that means it's stable. If they ever start switching places, even if they switch places and then they switch back and forth, that's bad. Well, that could be bad. That's called unstable. Now, generally, sorting algorithms can be made stable at a little bit of an extra cost. Some sorting algorithms are naturally stable, and like selection sort. As long as you use a less than, strictly less than, it will remain stable because you'll never put two things out of order. Is that true? Yeah, I think that's true, right? But quicksort, because you are doing the way that we presented it at least, quicksort, if you take this element and you throw it over here, and you take that element and you throw it over there, you could perturb things and switch things around, right? The way that we presented quicksort means that it was an unstable version. In order to get it to be stable, you might have to pay it a little bit of added cost. For that reason, a lot of libraries will either have a stable algorithm by default, or they'll allow you to call a different algorithm that's a little bit more inefficient but is stable, because you want that stability sometimes. Let me show you what happens when you don't have that stability. Let me sort it and resort it by year. Come on. Let me sort it and resort it by last name, first name. There we go. Right. Now, if I sort it once, would you expect it to be changed if I sort it exactly the same way again? No, but it happens. Right? Things get switched around for whatever reason. Right? What does that tell you? By the way, this is HTML and JavaScript. What does that tell you about JavaScript's built-in sorting algorithm? It is unstable, right? So I wouldn't use it. I think you can make it stable with an additional argument, but I didn't because that's the demo, right? If I made it stable, then I wouldn't be able to show you this weird perturbation here, right? All right. So that's total orders, artificial versus natural sorting, and sorting stability. Right? I meant to indent this stuff. Right? All right. That ends it. Any questions on searching, sorting? All right, well, then what I intend to do all next week is review. We could go into extra stuff if we want, but I think that I've got definitely enough review stuff. I've got old finals. We've got Advent of Code, and I've also I've put together a review exercise here. I don't know if people are interested or not in it, but with the release, I'm not a Pokemon player, right? I've never played the game in my life, right? But with the release of a new Pokemon game, I got it in my head for some reason that, well, what if we searched and sorted a Pokemon database? And so that got me thinking, how many Pokemon are there? Right? So does anybody know how many Pokemon there are? Over 1,000. Okay, that's because of the new game. I didn't know that until the only database that I could find had 800. Right? So with the new game, is there 1,000? Over 1,000? Okay. Anyway, I don't know when this goes back to, but this is an official database that I massaged a little and got rid of stuff of Pokemon. And then I randomized it so it's not in this nice natural order so that we could actually search and sort it, right? So these are all official Pokemon, right? And there are 800 of them. Over here, I found out that fans like to create their own Pokemon, all right? And so they're non-canonical Pokemon. And I took 5 random ones that I found on the internet, and I threw them into that database. So I've corrupted the official list of Pokemon here. Which one of these 805 are the false ones? Are you okay? I'd have to look at it. Would you be able to do it?
100%, yes.
Okay. I'll post this and see. Anyway, I have zero idea too, because once I copied them, I don't remember the damn names, right? Oh, what is it? Does any 262? Doublade? Is it not double laid? Okay. Steel Ghost or whatever. Okay. Anyway, what we'll do is we'll go through everything that we've done over the last 3 weeks. We're going to do a little bit of file I/O in order to process these CSV files. We'll load them up into structures that represent Pokemon so that we can sort them and we can search them. How would you go about doing this, by the way? For everyone in the fan database, you would check to see if it's in the official database. That means sorting it by some criteria and searching one day. Here's a key in the fan database. Can you find that in the official database? Using binary search. If you find it, that's an official Pokemon. If you don't find it, what is it? It's one of those fan-made ones. Right? And by the way, do you want to see a preview, or do you want to see a, let's see, review? There we go. I could do it in 1 second here, if you want to. Or do you want a spoiler? Spoiler. All right, fine. So, sort, official. All right, I'm just going to sort it in alphabetical order. All right, and pipe that into a, well, no, I'll go ahead and put that into one file, foo.csv. Sort fan.csv into bar.csv. All right, there we go. And then get diff, foo, and bar. So here are the 5 that I think I added. All right. Fangarm. All right, there we go. I just made the stuff up. I did not make up these names. Hexna, Mislith, whatever that is, and that one, and whatever that is, and then that one, that whatever that is. Right? So, kind of cool that you can use Unix-based stuff to do all of these problems that we've been doing in a matter of seconds, right? For example, what you could do then, you could use another tool called awk to do CSV files. I don't know, I forget how to do the delimiter, but what you could do is you could isolate all the names and then ignore everything else, or you could isolate, I think that these are hit points or something. Hit points, defense, attack or something. I'm gonna have to remind myself. But anyway, at any rate, you could use a tool called awk to isolate those things. You could use a tool called sort to sort them. You could randomize them. That's how I did that, right, by the way, right? Fan.csv, right? I'm going to randomize it every single time. See, it's different every single time, right? The R stands for sort it in a random order, right? Then once you've sorted it, you can grep it. You can search it for, I don't know, what's your favorite Pokemon? Spell that for me, please.
R-I-O-L-U.
That's probably enough. There they are. They're a fighting Pokemon with none for another category. 40? Isn't that kind of low?
Well, that must be one of those stats.
Okay. And then 70, 40, whatever that means. All right. So there they are. grep is another tool. You can search through using GNU regular expressions. Right? You can pipe all of these things together. That's what I'm doing with this pipe. This is a vertical bar here. And I could take 5, 10, 15 different Unix tools that all do one thing and one thing really well, and then pipe them, chain them all together to do some really complex computation without writing a single line of code. Right? If that kind of stuff interests you, definitely sign up for CSCE 251 next semester. It's an online 1-hour Unix course, right? Where you'll go through stuff like that, and maybe also PowerShell. Right? All right. Any questions? All right, you're not going to remember those 5 Pokemon anyway, right? No spoilers. I shouldn't have done spoilers. But somebody in the other section asked about some Unix magic that I was doing, so I thought I'd highlight that here too. All right. Have a good weekend.